Good day. This is the second video on chapter 5.3. I hope you listened to the first video about double integrals. Alright, now in year 1 we had the following notation, the integral from a to b fx dx. And we said that this is the net area under the curve y equal to fx on the interval from a to b. Now, in the previous video, we saw to represent a double integral. One way to do it is to write it as a double integral of f over region D and dA. And shortly we will mention that this is the net volume under the surface z equal to fxy, whose shadow is region D. Alright, but today we want to evaluate double integrals over trickier regions. So for trickier regions, we can use theorem 135 part 3, and the trick is to split the region up into several type 1 or type 2 iterated integrals. So to see this in action, let's do an example. So I'm taking example 145. So here D is the region in the first quadrant below y equals 3 minus x squared over 3, and outside the square with vertices 0, 0, 1, 0, 1, 1 and 0, 1. And the task is to write the integral, the double integral of x minus 2y over region D as an iterated integral or a sum of iterated integrals. So the first step would be to get to know what is region D. So if you sketch region D, it looks like this blue shaded region. And it's important to see where the parabola cuts the x-axis, which is 3, and it cuts the y-axis, which is 3. So I'm leaving that for you to verify. Now, this is the region over which we're going to do a double integral. Now, note that D is not of type 1. Remember, when you do type 1, you do vertical slices. So if I do a vertical slice here, it starts on the line y equal to 1, and it ends on the line y, on the curve y is equal to 3 minus x squared over 3. But if I make a vertical slice here, the blue region starts at the point y equal to 0, and the blue region ends at this point where y is equal to 3 minus x squared over 3. So you see, depending on where you slice it, the starting value could be either y is equal to 0 or y equal to 1. So D is not of type 1. Likewise, I'm leaving it for you to check. D is not of type 2. So we cannot write D as a single iterated integral. So we got to write this as a sum of iterated integrals. Now, the good news is we can split D up into 2 type 1 regions. And this is how you do it. So you can split the blue region into 2 type 1 regions, D1 and D2, as depicted in the diagram. So D1 is all the 2D vectors where x is between 0 and 1 and y is between 1 and 3 minus x squared over 3. D2 is all the 2D vectors xy where x is between 1 and 3 and y is between 0 and 3 minus x squared over 3. So if you do vertical slices, you can see that region D1 is of type 1 and region D2 is of type 1 as well. And now the reason why I'm having it in set notation is that it makes your job easy to now convert the double integral over D1 as an iterated integral and the double integral over D2 as an iterated integral. So let's quickly do that. So we can now say that the area of D is the area of D1 plus the area of D2. And so now D1 we can write as a double integral. The function is x minus 2y, and it's of type 1, so it's going to be dy dx. So we need to know x starts at 0 and x ends at 1. Y starts at 1 and it ends at 3 minus x squared over 3. So now we have written D1 as an iterated integral where the order is dy dx. Plus, now we do the same thing for D2. So we want to write this as a double integral. The function is still x minus 2y. It's type 1, so it's going to be dy dx. So now we need to know x starts at 1 and x ends at 3. So you can see why it was important to see where the parabola cuts the x-axis. That value is 3. And now we got to say, where does y start? Y start at 0. You see this lower bound is different to that lower bound. So now y starts at 0 and y ends at 3 minus x squared over 3. And so we've now written d as the sum of two iterated integrals, both of type 1. So it was important to draw the diagram to guide us to set it up correctly. So a few remarks. The fun part in this calculation is to convert the area into sum of two iterated integrals. And how did we do this? We split it up D into two type 1 regions, D1 and D2, so that the union of D1 and D2 is D and they don't share any mutually interior points. The calculation is an easy calculation, so I'm leaving it for you to verify that the double integral of f over region D works out to be this crazy fraction minus 1287 over 180. You can double check your calculation with the textbook on page 132 to 133. Alright, now for two theorems. So the first theorem helps us to show why double integrals are important, because double integrals help us to work out the volume of a solid. So if D is a closed and bounded subset of R2, and we have a function f that is non-negative, and we define solid E to be all the 3D vectors x, y, z, where x, y is an element of D, so that's a 2D vector and it's an element of D, and z lies between the surface z equal to 0 and z equal to fxy, where f is a non-negative function, then we end up creating a solid. So if you do this, you end up creating the solid that lies above the xy plane and in between till it touches the surface z equal to fxy. So that creates a solid E. And the volume, using Riemann sum, you can show that the volume of E is a double integral of f over region D, D being the shadow on the xy plane. So this is theorem 1. It shows you that the volume of certain solids, if it's in this form, can be written as a double integral with the correct region and the correct integrand. Now, building upon this theorem, I'm going to have my second theorem, which is a solid between two surfaces. So if f and g are maps from set D to R, and they are continuous, and f is less or equal to g for all 2D vectors x, y, in D, then the volume of the region f is a solid, and it's all the points in between these two surfaces. So characterized like this in set notation. So it is the solid between the graphs f and g. Then you can show using Riemann sum that the volume of solid f is equal to the double integral over region D of the top surface minus the bottom surface dA. So theorem 1 and theorem 2 is quite important because it demonstrates that certain solids, to calculate their volume, you can turn it into a double integral with the appropriate region and the appropriate integrand, so depending on what information is given. So I'm going to do examples where we get to see this in action and where we get to work out the volumes of certain solids in 3D. Alright, so the first example I've chosen is this example. So we want to find the volume of the region E in the first octant. So the first octant is all of the points where x is greater or equal to 0, y is greater or equal to 0, and z is greater or equal to 0. That is bounded by the surfaces with equations z equals 2 minus x squared, z equal to 1, and y equal to 2. So we have a solid or a region in R3. So we want to draw this in R3. So you saw how useful it is to draw the regions that you're trying to do the double integral over. All right, so to understand the question. Now I've broken this up into the first part where I have the surface z equal to 2 minus x squared and z equal to 1. And I want to know, when do they intersect in the first octant? So because we're in the first octant, we know that x is greater or equal to 0, we know that y is greater or equal to 0, and we know that z is greater or equal to 0. But if we want to know when the surface z equal to 2 minus x squared and z equal to 1 intersect, we ultimately have that 1 equals 2 minus x squared. So we get that x squared is 2 minus 1, which is 1. So x is equal to 1. Since minus 1 is negative, so we're not allowed to use the value minus 1. So we see that the two surfaces intersect at the following set of points. So if S is the intersection set, then we see that x has got to be 1. The y value, we don't have any conditions, so we can just say y. The z value has got to be 1, such that y is greater or equal to 0. All right. And so if we're only focusing on the surface z equal to 2 minus x squared and z equal to 1, and we want to know when do they intersect in the first octant, so this is a problem in 3D. So it will be all of the points 1, y, 1, where y is 0 or bigger than 0. All right. Now, let's try to draw this. Now, z equal to 1 is a plane. Z equal to 2 minus x squared is a parabolic gutter, which we did in chapter 1. So if you do the effort and you've sketched it, you will see that the diagram looks as follows. So z equal to 1 is this plane depicted here, which I'm shading now with green lines. And if you draw the parabolic gutter z equal to 2 minus x squared, you will get that part. And so we saw that the two planes intersect when x equals 1. So the two planes intersect when x equals 1. And so we want all of the points that is above the plane z equal to 1 and below the parabolic gutter. So the region that we want, all of the points in the first octant that I've tried shading here. So E, this is what we're after here. All right. So this is the region whose volume we want to calculate. Now, if we imagine we look at the shadow on the xy plane. So for this region, the shadow will be in a rectangle. And the rectangle will be, the x values are from 0 to 1, and the y values are from 0 to 2. All right? And remember, 1 was the answer we got when we calculated when the two surfaces intersect. We saw that x had to be 1. So the shadow will be region D. Great. So now we are in business, because now we can solve. And so by theorem 2, the volume of E is a double integral of f dA. All right. And so here, because we're using theorem 2, this will be the top curve minus the bottom curve. So it will be the top curve minus the bottom curve dA. So the region over which we're integrating is a rectangle, and we saw that the x value starts at 0 and ends at 1, and the y value start at 0 and end at 2. The top curve is the parabolic gutter, which is 2 minus x squared. And the bottom curve is z equal to 1. This is the bottom curve, and the top curve is z equal to 2 minus x squared. So f will play the role here of 2 minus x squared, and g will play the role of 1. So it works out that we now have to do the double integral from 0 to 1, 0 to 2 of 1 minus x squared dy dx. So now it's a double integral, and the region is a rectangle, so this is a very easy calculation. We work from the inside to the outside. So we first integrate with respect to y, so the integral of 1 is y, and the integral of x squared becomes x squared y. We replace y with 0 and then y with 2. And so if we do this, it now becomes, when I replace in 2, I get 2 minus 2x squared. And if I plug in 0, I end up getting 0. So the double integral converts into the single integral. And now we continue. The integral of 2, that's 2x, and the integral of that term becomes 2 over 3x cubed. And we use the FTC, and so by plugging in 1, we get 2 minus 2/3. And if I plug in 0, I get 0 minus 0. And if I simplify this, I get 4/3 cubic units. And so this is the volume of the solid. So the volume of the solid, we converted it into a double integral. So we first had to work out over which region are we integrating, and we got to have the correct integrand, and then we set it up, the double integral, as an iterated integral. We evaluated the iterated integral, and we ended up getting the value of 4/3. All right, so let's do one more example to see this in action. This is example 147. And the task is express the volume of the region E bounded by the paraboloid with equation z equals 2 minus x squared minus y squared, and the cone with equation z equal to the square root of x squared plus y squared as an iterated double integral. So we are going to do the same recipe as the previous problem. Let's first work out the intersection. After working out the intersection, let's do a rough graph of the region that we're interested in. And then we look at the shadow, so the region D over which we are doing our double integral. And then we convert this as an iterated double integral using theorem 2. All right, so let's start. Now, these two surfaces should look familiar, all right? If you think back to worksheet 1, these were the surfaces we played in worksheet 1, all right? So if you've forgotten the work in worksheet 1, so do have a peek at that. So let's quickly do the calculation. So we want to know when the two surfaces intersect. So that's my first heading. When do they intersect? So looking at the first equation, I see that x squared plus y squared equals to 2 minus z. This is from 1. And now looking at 2, we have that x squared plus y squared equals z. And now also remember, by looking at 2, we can also see that z has got to be greater or equal to 0. So the square root can never be negative. And now if x squared plus y squared is 2 minus z, and x squared plus y squared equals z squared, sorry about that, that should be z squared, we see that 2 minus z equals z squared, or z squared plus z minus 2 equals 0. Or we can factorize this. So we see that z plus 2z minus 1 is the two linear factors of this polynomial of degree 2. So we see z equal to minus 2, which we reject. Why? Since z is greater or equal to 0, so only z equal to 1 works. And so if we want to write the intersection in set notation, we can say it is going to be all of the 3D vectors x, y, 1, such that, so the z value is 1, so we see it's all the 3D vectors where the third component is 1, and because z is 1, we have that x squared plus y squared equals 1. And again, this should look familiar. This is what we did in worksheet 1. Great. So we've done, like the previous question, where the two surfaces intersect. So they intersect at all the 3D vectors x, y, 1, where x squared plus y squared equals 1. So now the next job is to draw these two surfaces so that we can get the region whose volume we are interested in. So 1 represents a paraboloid, and 2 represents a cone. So if you draw it, it looks like this. So it's like this ice cream cone. All right, you have the wafer part at the bottom and you have the ice cream part at the top. So E is all of the points that lies between these two surfaces. So it is all of the points touching the cone and above the cone, and it touches the paraboloid and below the paraboloid. So we want to work out the volume of E. So this is our task. We want to work out the volume of E. So it's good to know that this is the region whose volume we want to convert into an iterated integral. Now, as the previous problem, if you look at the region E and you project it down to the xy plane, so you look at the shadow. The shadow will be the red circle. And so in this case, it's quite clear that the shadow, or if you project it to the xy plane, it will be a circle. So in the previous question, the shadow was a rectangle. But for this question, the shadow is a circle. So let's quickly draw this. So we can quickly draw this. So the shadow will be, if we ignore the z value, then it will be all of the points in R2 whose radius is 1 centered at the origin. So this is D. So this is D given by all of, so if you want to write this in set notation, let's do that. That's fun. So D will be all of the 2D vectors xy with a property that x squared plus y squared is less or equal to 1. So we don't just want all of the points on the boundary, but we also want the points inside. So this is the shadow. And this is important because we need to set it up correctly as a double integral. So we need to know over which region we are integrating. And this is why it is worth your time doing this calculation. Great. So now we continue. And now we want to set this up as an iterated integral. All right. So we are going to say the volume of E equals a double integral over region D of the top surface minus the bottom surface dA. All right. So for this question, so here the top surface is the paraboloid, and the top surface has equation 2 minus x squared minus y squared. And the bottom surface is the cone, and so the bottom has equation square root x squared plus y squared. Great. And so the region over which we're integrating, as I said before, is a circle of radius 1 centered at the origin. And now the good news is that this is of type 1. Look at it. It is of type 1. If you draw vertical slices, it always starts at the bottom half of the circle, and it always ends at the top half of the circle. So no matter which vertical slice you draw, the starting point is always at the bottom of the circle, and the ending point is always where it ends on the circle. All right? And so if we do our slices, we can see that it's all the 2D vectors where x is between minus 1 and 1, and y starts somewhere and it ends somewhere. Well, let's quickly work this out. Y starts at the bottom curve and y ends at the top curve. All right? Can we work this out? Yes, we can, because we know that the equation of the circle is x squared plus y squared equals 1. So if I want to have y on its own, I can start by saying y squared equals 1 minus x squared. And so I can see that y is plus minus the square root of 1 minus x squared. So I can see the bottom curve has equation y equals minus the square root of 1 minus x squared. And the top curve has equation y is equal to the square root of 1 minus x squared. So that answers my question. It is all the 2D vectors where x is between minus 1 and 1. Y starts from minus the square root of 1 minus x squared, and y ends at the square root of 1 minus x squared. So having said D in this format makes it very easy to write this as an iterated integral. Remember, the task is to write this as an iterated integral. So now we can say the volume of E equals a double integral, the top function, which is 2 minus x squared minus y squared, minus the bottom surface, which is that. And we're going to write this as an iterated integral in the form dy dx. So x is starting at minus 1 and ending at 1. Y is starting at minus the square root of 1 minus x squared, and it's ending at the square root of 1 minus x squared. And that, ladies and gentlemen, is how you can convert this volume, so the volume of region E, which we saw in worksheet 1, as an iterated integral of the form dy dx. Great. Now, some of you might ask the following question. How on earth do we evaluate this double integral? Now, that is a story for another lesson. And that will come soon when we discuss polar coordinates in chapter 5.5. So if you're interested in working out the numerical value of the volume of region E, stay tuned for future lessons. All right. So my closing remarks. So please practice double integrals. And one part of the practicing is not just doing these calculations, but also setting it up. And you see in these two examples that I did, I broke it up into, if I have two surfaces, when do the two surfaces intersect? Then I make a rough sketch of the solid, whose volume I try to work out. Then I project to the xy plane so that I get the correct region that I'm doing my double integral. And then I correctly set this up as an iterated integral. All right. So if you want more practice in this, please do all of the problems in exercise 5.3. Thank you for listening. Have a good day.